Okay, so cyclone starts as a tropical disturbance, what is called depression in the Indian Ocean region. Then it's called deep depression, but in the Atlantic you would call it a tropical storm, and then it becomes a cyclone or a hurricane, and then grow into very severe, extremely severe super cyclone, typhoon, super typhoon, and so on. Let's do some simple calculations to look at potential balances within the cyclone. Assume that it's grown and it's in steady state, which is simplifying assumption. One of the critical non-dimensional numbers for looking at balances is the Rossby number, which some of you may have already heard of. Simply, it's the ratio of inertial to Coriolis force, or you can also think of V over L divided by F, where F is the planetary vorticity and V over L is the essentially relative vorticity, right? So a cyclone is essentially a vorticity balance system, so rotation, and it's moving in latitude, so it's changing planetary vorticity and having to deal with generated heat-driven vorticity, as well as there is flow towards the equator in the northern hemisphere on the western side, on the eastern let's see, counterclockwise. So on the western side you have flow towards the equator, and on the eastern side you have flow away from the equator, so you can use those with the latitude to see which way the vorticity has to which way the relative vorticity has to adjust to the changing planetary vorticity and so on. So long story short, Rossby number V over FL is what is used here for balance. So R0 Rossby number, if it's less than 1, then the system is in geostrophic balance. So in the absence of friction, we have pressure gradient force balancing the Coriolis. If it is close to 1, then it becomes the gradient wind balance that we just looked at. We will look at it again. And if Rossby number is much greater than 1, then we get into what is called cyclostrophic balance, where the pressure gradient and the centrifugal force can balance, and the Coriolis is much smaller in that case. Taking the simple figures from this education from some course at UIUC, you have a pressure gradient, so you have 1000, 1004, 1008 MB, so pressure gradient is in this direction, going from high to low. So you see the pressure gradient force there, and the flow adjusts. Basically, if it starts moving in this direction, Coriolis tilts it to the right, and eventually there is a balance, geostrophic wind, where Coriolis in this direction is balancing pressure gradient in that direction. Whereas in the gradient wind balance, you have flow that is along pressure gradient that is curved this way or this way. So depending on which way the Coriolis and centrifugal forces are acting, because you are moving along a curve, you have a centrifugal force to worry about. So in this case, the real wind is weaker than the geostrophic wind, so it is sub-geostrophic gradient wind balance. Whereas in this case, you have centrifugal force acting in the same direction as the pressure gradient force. So you have what is called super geostrophic wind. So you have real wind that is now stronger than the geostrophic wind. Okay, so that's the gradient wind balance. Just look at these figures, it's fairly straightforward. What happens in a cyclostrophic balance is that you have very strong pressure gradient and very strong winds along the curvature, and you have centrifugal force acting out, as you know from your basic physics. So in this case, pressure gradient can balance the centrifugal force, which is very strong, then the Coriolis is very weak. So you have what is called a cyclostrophic balance. So the question is, which part of the cyclone is balanced in which way? So look at the data here, 850 hectopascal wind observations in these dots for Hurricane Diana on 12 September 1984. Symmetric gradient wind shown here in the solid line, and the gradient wind change shown in this dashed line here. So this is looking at the change here at 6 hours, deduced from observed height fields. So you have geopotential height gradient, which can be used to derive winds. And obviously, when you look at the distance in kilometers from the eye of the hurricane, you have weak winds increasing to the eye wall where it's maximum, and then out to the longer distances, 150 kilometers and out, it drops off quite significantly. And here are the changes you are seeing in the winds every 6 hours as you go out from the eye towards the outer boundary of the cyclone. So winds are not changing much as you go out towards the edge of the cyclone, outside edge of the cyclone. You can also look at the radial profile of rotational winds for a theoretical tropical cyclone. So here we are looking at radial profile of rotational winds for the eye of the cyclone, so inside the radius of maximum winds. So you have initial initial profile here. It's just starting from, let's say, a tropical disturbance into a tropical cyclone. So you have weak winds as you go out away from the eye. The winds reach their maximum and then they drop off towards the eye, which is the quiet region. The winds can change because the strength changed a little, so you can see that the wind speeds got higher here and also towards the eye, but the maximum winds are the same here in this theoretical calculation. You can also change the size of the cyclone, so the velocity profile changes in a way that the wind speeds drop off more slowly than in the initial profile. Or you can intensify the cyclone, so intensity change will rapidly increase the maximum winds towards the eye of the cyclone, and then there is a much sharper pressure gradient into the eye and a much sharper drop off in the azimuthal wind speeds, so the wind speeds along the direction of the cyclone. Okay, so we can then look at these figures and pick off points, these two figures, and typical power of 10 values for wind speed and spatial scale for the three regions of this tropical cyclone can be picked off from the plots. So I about 10 meter per second over 10 to the 4 meters, so 10 kilometers. Storm strength of order 10 meter per second happens at about 100 kilometers, and the outer edge you have velocities dropping off to 1 meter per second, and that's happening at 1,000 kilometers. So from 10 kilometers to 1,000 kilometers. Okay, these numbers correspond to winds of 10 meter per second, V being greater than or equal to 10 meter per second and less than 100 meter per second over spatial scales of 10 kilometer for the eye, which has the sharpest pressure gradient towards the wall. V is greater than 10 meter per second over a spatial scale of 1,000 kilometer for the storm force wind area, so the size of the cyclone over which the storm force can be felt. And V is less than 10 meter per second over a spatial scale of greater than 1,000 kilometers for the outer region of the storm. Recalling that a degree of latitude is roughly 100 kilometers, right? These numbers are consistent with the figure 10.9, which is what we are looking at here in terms of the scale changes over distance. Okay, so it depends on the strength. To quickly do some calculations, we can look at Rossby numbers. Assuming a latitude of 15 degree, cyclone has formed, has moved away from the cyclogenesis region, let's say, gives us F of 4 times 10 to the minus 5. I think you know how to calculate Coriolis at a given latitude. 2 omega cosine phi, or is it sine phi? Make sure I'm doing it right. Cosine would go to sine phi, so 2 omega sine phi. Again, for an order of magnitude analysis, we round this value of f to the nearest power of 10. So we can use f 10 to the minus 5. In the I, we have, using v and fl, we have a Rossby radius of 100, non-dimensional. So there the cyclostrophic balance is happening. So the pressure gradient is so strong and the velocities are strong enough that the centrifugal force is balancing the inward pressure gradient force, and the storm strength is at the Rossby radius of 10, where we have gradient wind balance. So centrifugal and Coriolis together are balancing the pressure gradient force, and at the outer edge of the cyclone we have Rossby radius dropping to less than 0.1, so we have close to geostrophic balance. Obviously this will depend on how strong the cyclone is. So if the cyclone has 40 meter per second top wind speeds, then I has 40 meter per second wind speed with over 50 kilometers. Storm strength is dropping to 15 meter per second out to 150 kilometers, and at the outer edge we have 10 meter per second at 500 kilometers. So the Rossby numbers at similar f will give us 800, so still cyclostrophic balance, but we are at 50 kilometer here. Storm strength at 10 Rossby radius, Rossby number, sorry, so is still in gradient balance, and the outer edge we still have Rossby number of 2, so we don't have geostrophic anymore for a strong cyclone. We are getting a gradient balance out to 1000 kilometers. Okay, so strength of the cyclone determines again how the balance is happening from the eye to the outer edge. Pick a weaker cyclone at 20 meter per second, again 20 meter per second at 120 kilometers. So the strength of the cyclone also determines the size, right? So we are going here from 150 to 500, whereas here we're going 120, 150 and 500. Why? Because stronger the cyclone, the stronger the drop in the pressure in the eye and tighter the eye. So the eye here is 50 kilometers, and here let's see, here we had 10 to the 4 meters, so almost 10 kilometers. So based on that, we have again a cyclostrophic gradient and geostrophic balance. So the main point to remember is that the balances are typically cyclostrophic, gradient wind balance and geostrophic balance, but this depends on the size of the storm, which depends on the intensity of the storm and the size of the eye and the pressure gradient and the drop off of the wind speeds out to the outer edge of the cyclone. Okay, so it gives you a good sense that balance is not the same across the cyclone, and it's not the same in all cyclones. It depends on the intensity of the cyclone and the size of the cyclone. Okay.